Okay, so we have opened our schematic, and when you go to launch and click out layout Excel, when you click out layout Excel, the layout suite Excel loads in. Now basically the layout has already been created. So if you can see here, these are NMOS. Sorry, I'm really sorry. These are PMOS in sequences, and these are NMOS. This is the horizontal rail given to VDD. This is the horizontal rail that has been given to ground. The blue one indicates metal one layer. All right, the green can be given as is said to be the poly layer, and these small blocks that you see, these are via. All right, so basically, when you come from schematic to the layout, what you have to do is you have to go to connectivity, you have to click on generate, and you have to click all from source. When you click all from source, what you'll get is you'll have all the input pins. Like here, this is D. Let me see if I can, yes, display pin names. And okay, I think because it has already been created, the pin names will not be displayed. Let's see, by changing the axis maybe we'll able to see. Hmm, okay, so it's still not being displayed. Anyways, so these are wires. Okay, see, the input is a metal one. All right, metal one cannot be directly connected to the poly. So we use a wire. You put a wire, you drag the poly here, you drag the metal one here, and they are connected through it. Okay, and see, metal one and poly layers, they can be directly placed one over the other. All right, because they are in a different, if you see the 3D representation, it is different. However, a metal layer cannot cross a metal layer directly. Let's see, for instance, here. The poly was supposed to pass from here, but it cannot pass directly because there's another poly layer which is going through here. So this was interfere the connection. All right. So what we basically do is we use a wire and then we place a metal one layer. All right. So this is how the layout has been done. Layout follows schematics. The next part is you go to Asura and you run a DRC check. Okay, you go to DRC, you select your technology GPDK 90 nanometer, then you can apply. Okay, okay. So the DRC run and check. Now see, DRC plays a very important role. Press on yes, no DRC error found. See, DRC basically stands for design rule checks. This means that there are certain rules that you have to follow. All right. A metal one layer has a particular area, that there's a minimum area that this layer has, is meant to have this much area at minimum. All right. You cannot keep it less than that. There's a minimum separation between the poly layer and the metal layer. There's a minimum separation between a metal layer and a metal layer. There's again a minimum area for a poly layer. Okay, so in a design rule checks, when I had created the layout, there were several errors when you run the DRC. All right, so you have to read them and you have to understand that okay, it requires poly to poly area greater than zero point 0.1 micrometer, it requires metal to metal area less than 0.7 meter, something like that. So you have to read it and sometimes you have to make changes accordingly. All right. Now, at the moment, we are not looking forward very much at optimizing our layout, reducing the areas, reducing the wiring, because all of this that you see here, this creates delay. This increases delay in the post layout simulation. We will be looking at in our next video when we'll talk about pre-layout and post-layout simulations. All right. So now what you have to do is after this is done and after DRC is done, then you have to again go and run LVS. Now see, when DRC is compiled and you have no DRC error, all right, that does in most of the cases your LVS will be successful. You will be having a perfect LVS. All right, but it is not necessary that if you do not have a DRC error, you will not have an LVS error. I'll provide you an example. See, the thing is, let me show you first. Let me run LVS first. So you click on LVS, you select your technology 90 nanometer, and you press on apply. LVS overwrite. Okay, the LVS is running. It usually takes a little bit of time to display the LVS results. Okay, so see, as of now, there is this error. This is what I wanted to show you, that there's an unbound pin. All right, the LVS run, one cell had pin mismatch, no extraction problems were found. All right, no warning, no errors. There's one pin error, and that is not much important. Sometimes it happens because when you see basically what LVS is all about. LVS is all about schematic versus layout. The meaning of LVS is layout versus schematic. If you see, there are six MOS, there are six MOS, there are five MOS, there are five MOS. There's no mismatch here. There's no mismatch as net. TSPC, VSS, summary, error type, unbound pin. Okay, so this is not much of a problem. It's just a simple error. Okay, so basically, LVS error occurs when your layout doesn't match to the schematic. Now, since we made some changes during the schematic, there were some errors. Earlier, when I will show you when I had compiled this, uh, the same. So, as you can see that this is how it appears, that there are no DRC violations and there are no LVS issues. All right. This is of the time when I had run the simulation, but since we have made a lot of changes in the schematic, there are some probable errors. There's one unbound pin because of which the error happens. Now what you do is you go to Asura again and you run Quantus. All right. You run Quantus, and now what we have to do is we have to do the RC extraction. So please keep in mind you have to make no changes here. Your technology will be kept as GPDK 90 nanometer. Output, it will be extracted view, and you have to name your file. Then you have to make no changes here. You have to come to extraction. The extraction type must be RC. Then again, no changes here. Net selection must be full chip, all nets. All right. Once you do this, you'll click on apply and it is extracted. Okay. So we had completed the RC extraction from the layout. Now see, when you'll do that, you can go to file and open, and you can select the file and that extraction file name that you set here. So this will open. Now basically if you see, you'll notice the capacitances, the values, and if you have to have a clear idea, you can go to options, display, nets. Now when you select nets, you see you'll get all the links, how they are linked, how the capacitor, the resistors, what are the nets, how the nets are connected. So with this, we completed schematic, simulations, symbol creation, implementation and simulation, layout, DRC checks, LVS checks, and RC extraction. Now, what the next part of the video follows is that we'll do a pre-layout simulation and a post-layout simulation. Pre-layout simulation will be done, which is basically a schematic simulation. We'll measure the delays and I'll tell you the reason behind the difference and everything. And then we'll use this RC extracted values. We'll configure it into our schematic values and do the post-layout simulation. All right. And after that is our last step, that is the GDS2 generation. Thank you. That's it for this video.